Hi dear children, in this video we are going to discuss two theorems in the chapter circles. First theorem, the tangent at any point of a circle is perpendicular to the radius through the point of contact. The tangent at any point of a circle. In this case, just look at the figure. The tangent is xy. That is perpendicular to the radius through the point of contact. This tangent touches our circle at P, then the radius through P, that is our OP. Now we need to prove xy perpendicular to OP. For that, I'm going to take one point Q on xy. Q on xy. Okay, I'm going to take one point Q on xy. Now, if that point Q lies on the circle, what will happen? If that point Q lies on the circle, what will happen? Is it possible? Is it possible to happen like that? No, that is not possible. If this Q lies on the circle, then we will have 2 points which is common to our xy and circle. One is P and other one is Q, right? If that Q lies on the circle, then that Q and P is common to our circle and xy. Then this xy becomes secant, but we took it as tangent. So that Q cannot be lies on the circle. Okay, that should lies outside the circle. Okay, and this M lies on the circle, and this OM and OP are equal, right? Why? OM is equal to OP. Both are radius of the same circle. OM and OP are the radius of the same circle, so OM is equal to OP. Now, OM is equal to OP and OQ is greater than OM, right? OQ is greater than OM. Okay, OM, still this we have OM and some more distance is there. So OQ is greater than OM. That means OQ is greater than OM and OP are equal. OQ is greater than OP. This OM we can replace it by OP because OM and OP are equal. OQ greater than OP. So the shortest distance here it is OP. Suppose we took one point from this side. Then that point also should lies outside the circle. If it lies on the circle, then P and that point will be common to circle and our line xy. Then this xy become secant. So if you took any point, on this xy, that should lies outside the circle. That means that distance should be greater than our OP. Then this OP is our shortest distance. OP is our shortest distance of all the distances of the point O to the points of xy. That means OP is perpendicular to xy. Listen, to prove this theorem, we took one point Q outside the circle and it lies on the line xy. And if this Q lies on the circle, then this line xy becomes secant because P and Q is common to this circle and this line. So that point Q lies outside the circle. If you took any point on xy, that point should lies outside the circle. Otherwise, this xy becomes secant. And this OP and OM are equal because they are radius. Okay. Clearly, this OQ is greater than OM. And I am going to replace this OM by OP because that two are equal. It happens for all the points on xy except this P. So that means that OP is the shortest distance of all the distances of the point O to the points of xy. So OP is perpendicular to xy. Clear? Now, my question is, how many tangents you can draw to a circle from an external point? How many tangents you can draw to a circle from an external point? This is our circle and we have an external point here. Let it be P and the center of the circle O. And how many tangents you can draw to the circle from that P? One tangent like this, right? If you try to draw tangent like this, then that is become a secant. Then just opposite direction. So we can draw two tangents from an external point to the circle. And here comes our second theorem. Second theorem says that the lengths of tangents drawn from an external point to a circle are equal. The length of tangents drawn from an external point to a circle are equal. That means here our tangents are PQ and PR, that's drawn from an external point to a circle. We need to prove PQ equal to PR. We need to prove PQ equal to PR. Just join this OP, OQ and OR. Now, OQ is perpendicular to OP. Why? By using that first theorem. Radius and tangent are perpendicular. Radius through the point of contact and tangent perpendicular. And here OR and P are perpendicular. OR and P are perpendicular because this OR is the radius through the point of contact of PR. Okay. Now, we are going to consider the triangle OQP and triangle ORP. Triangle OQP, triangle ORP. Okay, these two triangles are right angled triangles. And in this triangle, OQ is equal to OR, right? OQ is equal to OR because they are radius of the same circle. And OP is equal to OP because that is common. That side is common to these two triangles. Now, by using RHS, we can say that these two triangles are congruent. By using RHS, we can say that these two triangles are congruent. If these two triangles are congruent, then by using CPCT, we can say that PQ equal to PR. PQ equal to PR. Okay, just listen. This P is our external point and from this P we can draw two tangents to the circle. And we need to prove PQ equal to PR. That means the length of the tangents drawn from an external point to a circle are equal. Very important theorem. For that, I am going to just join those OQ, OP and OR, and this OQ is perpendicular to PQ. OQ is perpendicular to PQ because this OQ is the radius through the point of contact. And OR is also perpendicular to PR because this OR is also a radius through the point of contact. Then these two triangles are right angled triangle. And in this triangle, OQ is equal to OR because they are radius of the same circle. And OP is equal to OP because they are common. Now by using RHS, we can say that these two triangles are congruent. If these two triangles are congruent, by using CPCT, we can say that PQ equal to PR. That means the length of the tangents drawn from an external point to a circle are equal.